So welcome to the 84th Theoretical Physics-Colloquium by Professor Xu-Guang Huang from Fudan University in China. He received his PhD in 2008 at Tsinghua University. After PhD, he had several postdoctoral positions, one at Frankfurt University between 2008 and 12, and then at Indiana University between 2012 and 13. He has the faculty position at Fudan University from 2013, and now he is a full professor there. His research interests include QCD matter at high temperature and density, heavy ion phenomenology, neutron star physics, cold atomic physics, and recently one of his main focuses was on spin polarization phenomena and heavy ion collisions, and that's today's topic, which is spin polarization and spin transport in quark-gluon plasma. And with that, I'll give the microphone to Xu-Guang.
Okay, thank you. Thank you, Igor. Thank you for the invitation and for the introduction. I'm going to talk about the spin polarization and the spin transport in the quark-gluon plasma. So here is the content of my talk. So first I will give an introduction and also the motivation why we study the spin polarization and the spin transport in the quark-gluon plasma. This is actually now the spin polarization can be used as a special probe to the quark-gluon plasma. Then I will talk about the current theoretical understanding of the spin polarization in the heavy ion collisions. So you will see that there are some problems, there are some puzzles. With that, I will go to the third part, which is the spin hydrodynamics, which I think will be very helpful for us to understand those puzzles. If the time permits, I may also discuss the QCD phase structure due to the rotation. So finally, I will summarize. Yeah, this is the schematic phase structure of the strong interaction matter. So at low temperature and low ion density, so we have the usual hadrons. So we have the hydronic matter. With the increasing temperature, when the temperature is higher than some special value around the lambda QCD, around the 200 MeV. So we will have a phase transition or crossover, depending on whether we have quarks into a deconfined phase, usually called the quark-gluon plasma. This quark-gluon plasma can be created, for example, in the early universe or in some interior of some compact object like the neutron stars. But on Earth, the only way to produce and to study the properties of the quark-gluon plasma is the high energy heavy ion collisions, like the relativistic heavy ion collider in US and the Large Hadron Collider in Europe. So in these colliders, two ions, like the gold nucleus and the lead nucleus, are accelerated to a very high speed and then collide. And in such a way, a high density of energy is reached, and the deconfinement condition is reached, and the quark-gluon plasma is created. This quark-gluon plasma is very hot, and they expand and cool down into some lower temperature below the lambda QCD. Then those quarks and the gluons hydronize into hadrons, and those hadrons finally fly into the detectors and finally be detected by the detectors. So if we want to understand, if we want to investigate some properties of the quark-gluon plasma, we have to have some way to have some specifically defined observable from these final state hadrons. And from those observable, we can extract some special properties of the quark-gluon plasma. So those special observables are the probes of the quark-gluon plasma, like the hard probes and the soft soft probes like the jets and also some distributions. So here I give you an example. This example is the isotropy in the charged hadron spectrum. So let's consider non-central collision. So after this non-central collision, the quark-gluon plasma is formed in this almond-shaped regime. This regime is anisotropic, and so the pressure gradient is anisotropic. The pressure gradient is maximum in this direction. This direction is the exponent direction. So the quark-gluon matter will expand mostly in this direction, and finally this will drive an anisotropy in the final state momentum space distribution, like showing here. So this distribution is anisotropic, so it can be decomposed into different Fourier components, and those Fourier coefficient here, the V1, V2, V3, and so on, are the so-called harmonic flow coefficients. So they characterize how the anisotropy the charged hadron spectrum is. So here is the experimental result from the Atlas collaboration about the charged hadron V2, V3, and so on. Indeed, you can see that there is a finite V2, V3, and so on with very high accuracy. Okay, so the hadrons usually, for example, the pions carry also spin. Also, there are vector mesons. So we could ask, so can there be some spin-related probe? So namely the spin probe instead of the usual probe like the V1, V2 for charged hadrons. Could we have the spin probe to the quark-gluon plasma? The answer is yes. In 2017, STAR collaboration reported a very interesting measurement, which is the lambda spin polarization. Actually, the global lambda spin polarization. The global means that the polarization is measured as a whole. It's not distributed into some like aspect angle or PT or and so on. So they measure this lambda hyperon spin polarization as a function of the beam energy square root of S, and you can see that there is a finite spin polarization for lambda. So the polarization is defined in this way. So because spin is a vector, so what is measured is the projection of this vector into the direction perpendicular to the reaction plane. So here this y direction. Thus they measure the number of the lambda with spin up minus the number of lambda with spin down divided by the total number of lambda. So this is the definition of the spin polarization. So why they measure the lambda hyperon spin polarization, not like the proton or neutron, because there are more protons and neutrons created than lambda. The reason is that lambda decays through a weak interaction and it's a parity violating. So in the lambda raster frame, if you can measure the direction of the daughter proton, basically you measure the direction of its spin direction. So yeah, that's why they measure the lambda spin polarization. So in this year, they also reported the result of other hyperon polarizations. They reported the cascade minus and omega minus global spin polarization at 200 GeV. They also have some result at 27 GeV, but not sure. Also, the Hadis collaboration also reported, as well as STAR collaboration, reported a spin polarization of lambda at a very low energy, quite near the production threshold, but it's also observe a finite spin polarization. So the idea of spin polarization was first proposed by Liang and Huang, and later also considered the consequence in experiment by Voloshin. And now this exciting measurement show that indeed we have the spin polarization of lambda hyperon and also other hyperons. So this could be used to probe some special properties of the quark-gluon plasma. So if we do not look at the total number of lambda, instead, if we look at the lambda from some specific kinematic region, like the azimuthal angle phi, pt, rapidity eta. So here, for example, if we look at the lambda spin polarization from some azimuthal angle phi, this is the polarization definition. In this way, you can study the spin polarization, the dependence of the spin polarization as a function of phi. This is a differential spin polarization measurement. Sometimes it's also called the local spin polarization. So here I show you the star result, that the spin polarization for lambda as a function of azimuthal angle phi. So you can see that there is a non-trivial phi dependence. Also, the polarization along the beam direction, here the z direction, as a function of the phi. You see this is a interesting sine 2 phi dependence, and this sine 2 phi dependence is also reported by Alice collaboration this year.
We have a question.
Yep.
Rajim, do you wanna?
Yeah, just a small question. For this transverse polarization, I can say that is it okay to say that this global polarization is zero in large phi?
It is within the error bar here. You can see that within the error bar.
I can see that. So on the average, I can say that this is zero in large phi if I extrapolate.
This is not large phi. This is a pi half. Okay,
Phi
yeah.
is angle.
Phi, yeah, phi minus psi 1.
Yeah. This is an angle. So the polarization will be first large. If you go to the direction perpendicular to the reaction plane, it is very small. And if you go further, it becomes larger again.
Okay.
From this non-trivial phi dependence, we can extract the spin harmonic flow coefficient. So here, this F2 coefficient and this G2 coefficient in front of the sine 2 phi and the cosine 2 phi terms. From those measurements, you can see that the experimental measurement gives F2Z larger than 0 and G2Y larger than 0. Okay, so with those we can say that okay, we have a non-trivial spin probe to the quark-gluon plasma. I think this is very exciting because if we look at the condensed matter physics, we can realize that first we know how to use electricity to do something for us. For example, the laptop, the lamp, the washing machine. This already know for I think more than 100 years, but quite recently, mostly in the past like 3 decades. So we know how to use the spin current to do something for us. For example, to build the hard disk, to build the spin memory in some special devices, and also this spin current can also be used to detect some special structure, vortical structure in the fluid matter. The same thing happens in hadron collisions. So before we have this, let me call it the electronics in hadron collision. Namely, we use the charged hadron like multiplicity and charged hadron, V2, V3, and also other observables constructed by using the charge of the hadrons. So now we see that we can use the spin of the hadron to construct some observables to probe some property of quark-gluon plasma. So this is the subatomic spintronics in hadron collisions. But the question is, what really the spin polarization observable probe? So what is probed in quark-gluon plasma by the spin polarization? So I think this is quite naturally to think that what is probed is the vorticity. So from this figure, so if you rotate a cup of coffee, the constituent particle in this fluid will feel this orbital angular momentum. And due to the spin orbital coupling, the spin will be polarized. And this can be formulated in this effect Hamiltonian given by the S dot rotation term. So namely, if you have a rotation, this rotation will polarize the spin. So with this picture, if you consider a thermal equilibrium state of spinful particle, you can easily calculate the spin polarization, which is given by omega. Omega is the rotating frequency divided by 2 times temperature. Okay, then is there really vorticity in hadron collisions? The answer is also yes, because for non-central collision, the system carry a large angular momentum. So here I give an estimate for the gold-gold collision at 200 GeV with the impact parameter 10 Fermi. So you can easily estimate the angular momentum of the system is around 10 to the 6 times h bar. So this is a big angular momentum. If you compare this with a single hadron spin, which is of the order of h bar. So this is a very large compared to the spin. And after the collision in the quark-gluon matter, a portion of this angular momentum will be captured by the quark-gluon matter. And in this case, this portion of angular momentum can be formulated as the integrate as the momentum inertial I times the vorticity integrated over the space. So this omega is the vorticity. Because the system size is very small, so the momentum inertia is small. So you expect that this vorticity could be very big. And indeed, from some more more precise calculation using some transfer model or using some hydrodynamic model, you can really calculate the vorticity. And you can see that the vorticity is really large. It is of the order of 10 to the 20 to 10 to the 21 per second. Also, the interesting feature here is that the vorticity decreases when you increase the collision energy. So this is a relativistic effect because at the higher and higher collision energy, the system becomes transparent in the mid-rapidity region with the capacity of carrying angular momentum decreased. So you have a smaller vorticity. If you compare the strength of this vorticity to the vorticity in other fluid, you can realize that this is the vorticity that's much higher than any other vorticity that we know in nature. So that's why sometimes we see that in hadron collisions we created the most vortical fluid. So there are many different calculations by using different methods and different models. Basically, those calculations confirm each other that there is a very large vorticity. But this global angular momentum is not the only source for the vorticity. The thermal medium expands inhomogeneously. due to this inhomogeneous expansion, so there could be some special vorticity, vertical structure emerge. For example, the system expand in the longitudinal direction, but inhomogeneously in the transport direction. Then you will have this smoke ring-like vorticity with opposite, with different direction in forward and backward rapidity regime, like what's shown here from the simulation from this group. And also the system expand in the transport direction, like the X direction, but inhomogeneous in the Y direction. Then you can realize that there is this special quadruple type of vorticity, which can also be confirmed by using the numerical simulation. So you could expect that this special shape of the vorticity would be the source of this special sine 2 phi dependence of the local spin polarization. Yeah, but the story is not that simple, as you can see that the local polarization is very complicated. Okay, so with this, we want to understand the spin polarization measurement quantitatively. Then first, we need a theoretical tool to describe the spin polarization. So let's consider spinful a main body system of spinful particle. So in this case, the spin 1/2 direct fermions. So we consider a local Gibbs state, which is obtained by maximizing the von Neumann entropy under the constraint that locally we have the angular energy density and the momentum density constrained by the true physical value, and also the local angular momentum is constrained by the physical actual value. So under those constraints, from the maximum entropy, you can obtain this local Gibbs state. Theta mu nu is the stress tensor and momentum tensor. So for at this stage, we don't need to specify whether it's canonical or not. But for the following use, we call this the canonical stress tensor. So here, this sigma mu rho, sigma is the canonical spin tensor. So with beta and mu two Lagrangian multiplier, they will be this the thermal flow, and mu will be called the spin chemical potential. With having this local Gibbs density operator, you can calculate the Wegener function defined this way. Once you obtain the Wegener function, you can calculate the spin vector, canonical spin vector in the phase space. Okay, so which is defined by the canonical spin tensor times the Levi-Civita tensor. Yeah, so the calculation finally leads to this expression. The mean spin vector in phase space. So here, I already take the on-shell condition. And what it shows only for the particle branch. There is the same expression for the anti-particle branch. So here, EP is the energy of the particle, mu is the spin chemical potential. This Cassi tensor is the thermal shear tensor. And this delta mu is the difference between the spin chemical potential and the thermal vorticity. And the thermal vorticity is defined this way.
Xu-Guang?
Yes.
A quick question. Do you have a tacit assumption here that the particles are heavy and sort of kind of like non-relativistic? Because you seem to separate particle and antiparticle branches, which might be possible only if you have non-relativistic regime.
In principle, yes. Right. Although of course the whole formalism does not rely on whether I take the non-relativistic approximation or not. But here, indeed, I take only the particle branch by integrating the energy from 0 to infinity to pick up the particle branch. So there is a anti-particle branch. If the particle and anti-particle, if the mass of the particle and the particle is small, because we should add these two contributions together to get the spin vector. Yeah. I mean the whole formalism is accurate. I do not need to make this approximation. For example, if I also add the anti-particle contribution, then the expression is full. So now let's consider this hyper surface C. So if this is the phase-out hypersurface for both spin and the particle, then we can integral this mean spin vector in phase space over this hypersurface and obtain this formula. So this formula is a Cooper-Frye type formula, because which means if you have the distribution of the spin vector in phase space, this formula will tell you after the hydrodynamization the spin polarization in the momentum space. So far, so good. But to really calculate the spin polarization, we need to know the spin chemical potential of mu, the temperature, and also the velocity. For the temperature and the fluid velocity, we know that we could have well established the hydrodynamic model or stress model to do the calculation. But so far, we have no knowledge about the spin chemical potential. Thus, to use this formula, we have to know we have to make some assumption for the spin chemical potential. So one possible way is that we take the assumption that the system is very close to a global equilibrium, so that we can use the global equilibrium condition. In this situation, the thermal shear is 0, and the spin chemical potential is equal to the thermal vorticity. So with these two conditions, the above formula is simplified into this form. This very useful form was first derived by Baccadini, and later on by other groups by using different methods. This formula is valid at a global equilibrium. The good feature of this formula is that it's very easy to use, because it only depends on the thermal vorticity, which is easy to calculate. But in this formula, the spin polarization is enslaved to the thermal vorticity. So the spin degree freedom is not dynamic, but totally determined by thermal vorticity. So using this formula, we can actually explain the data for the global polarization quite well. So here I show you some theoretical calculation of the global polarization of lambda from different methods, but basically based on the vorticity interpretation. So they work pretty well. Also for the cascade and the omega hyperon polarization, also by using this vorticity interpretation, you see that so here is the primary polarization, which also expands from this curves, and also here is when the fade down effect is considered, you will find that the cascade polarization is enhanced and the lambda polarization is saccharized. But overall, those calculations shows that the theory calculation using the vorticity can fit the experimental data. So namely, the vorticity is the bridge that connect the global angular momentum to the final observed global spin polarization. However, if you apply the same formula to the local spin polarization, so namely the spin polarization as a function of phi, you found a big disagreement with the experiment. So the experiment gives that the F2 coefficient here is positive, but the theory gives negative value. Similarly, for the G2Y, the theory gives negative value, but the experiment gives the positive value. So we have a problem here. To solve this problem, there have been lots of efforts. I think the first thing is to understand the vorticity. I think this we already understand the vorticity quite well, and also we need to understand the fade down effect because a lot of lambda that's measured from the experiment are actually from the fade down decay from some heavier particles. And also, in addition to that, we need to understand the dynamics of the spin, also whether some other contribution to the spin polarization. So first, let's consider the fade down contribution. So about 80% of the final lambdas are actually not primarily produced, but from the decay of mainly the sigma hyperon and the cascade hyperons. And from this decay, the spin can be transferred from the mother particle to the daughter lambda, and some of the transferring process can flip the spin polarization. Thus, this gives some possibility that to solve the local spin puzzle. However, from the numerical simulation, so you can see that this is not the case. Although most of the measured lambda is from the fade down decay, but the contribution, the fade down effect to the lambda is very small. It only suppresses about 10% of the primary lambda spin polarization. So this does not the main reason for the local spin puzzle. So let's consider other possibility. Recall that we have this spin polarization formula, and now we don't know the spin chemical potential. But let's make some assumption. So in the previous case, we assume that this spin chemical potential is given by thermal vorticity. But let's relax this condition. Let's consider spin chemical potential is still determined by the fluid velocity and the temperature, but not necessarily by the thermal vorticity, but some special combination of velocity and temperature. Could be other types of vorticity. For example, the temperature vorticity. And with this temperature vorticity, and also with the vanishing shear condition, as you can see, interestingly, it could explain the data with both the longitudinal local spin polarization and the transverse spin polarization. Maybe partially the reason maybe is that this temperature vorticity has a interesting property that in the ideal fluid, it is conserved. It is frozen in the fluid cell, so it will expand with the fluid. So maybe this reflects some feature of the spin dynamics, so that they face the data. But overall, this does not have very clear physical underlying physical reason why we should use the temperature vorticity. Then let's try other possibilities. An interesting possibility was considered by these several groups this year. That is there is this shear contribution, which is very interesting because you see here this thermal shear tensor can actually contribute to the spin polarization, which was first realized by these two groups. And with this, make the calculation and with some assumptions. So for example, here the assumption is that the lambda polarization is totally determined by its strange quark constitute polarization. And the polarization in this calculation is that the freeze-out hypersurface is isothermal. So with those, you can see that the calculated polarization can in some cases it can fit to the data. But also there are some other studies that found that this may not be the case. For example, this paper found that the shear contribution almost cancel the vorticity contribution. So which means I think we need more study to understand the shear contribution. But anyway, I think so far we do not have a clear understanding of the local spin puzzle. So very promising way to understand this is perhaps the dynamics of the spin degree of freedom. So maybe we really need a dynamic theory for the spin degree of freedom. So this is the spin hydrodynamic framework, for example. So this the spin hydrodynamics is the framework to describe the collective spin dynamics, in which the spin is treated as a quasi-hydrodynamic variable. So this framework has been widely used in non-relativistic system, in non-relativistic spintronics, like what I show here, and also in what is called a macropolar fluid. So the macropolar fluid is those kind of fluid, in which case the fluid cell can have some internal degrees of freedom inside as the usual fluid, we treat the fluid cell as a point. So in the macropolar fluid, the fluid cell could have like the rotating degrees of freedom and so on. So its formulation would be similar to the spin hydrodynamics. So let me remind you that what is hydrodynamics. Hydrodynamics is a low energy effective theory for the conserved quantities. In the homogeneous limit, because the quantity is conserved, it does not disappear. So the relaxation time for this quantity is infinite. So when the system is slightly inhomogeneous, this quantity could move from some place to other place, and this movement is described by the hydrodynamics. And the hydrodynamics is thus can be constructed by using the gradient expansion. And the typical hydrodynamic modes are those conserved quantities like the energy density, momentum density. If you have a baryon number, then the baryon number density. So for the spin, if spin current is conserved, the hydrodynamic equation is simply given by these three conservation laws. The first is like a baryon charge conservation. The second is the energy momentum conservation, and the third is the spin conservation. And to formulate a hydrodynamic framework, we can just expand this J, theta mu nu, and sigma mu nu rho, order by order in a gradient. Those is the constitutive relations for the spin hydrodynamics. And this leading order terms would be correspondent to the ideal hydrodynamics. Actually, this framework was first considered by Shovkovy and his collaborators. But the spin is not conserved in general, because what is conserved is the total angular momentum. Spin is just a part of the total angular momentum. So from the conservation of total angular momentum, you'll see that the partial mu sigma mu nu rho is equal to the antisymmetrical part of the energy momentum tensor. So it's not conserved. So strictly speaking, spin is not a hydro mode. And also, this equation describes the spin orbital coupling. So there could be the conversion between the spin angular momentum and orbital angular momentum described by this equation. And this conversion is usually dissipative. So we need to formulate such a spin hydrodynamics. In this framework, spin is not a strict hydrodynamic mode. But if the relaxation time for the spin degrees freedom is much longer than the relaxation time of other non-hydro modes. So here, the relaxation rate of spin is capital gamma S, and other non-hydro mode realization rate is capital gamma. If capital gamma S much smaller than capital gamma, although spin is not a strict hydrodynamic mode, we could formulate a theory in which we could have a spin degrees freedom and also the true hydrodynamic mode. So in such a way, we could form a quasi spin hydrodynamics. As I said, because spin is not conserved, it could change with the orbital angular momentum, which will induce some dissipative effect. So what we want to have is the relativistic dissipative spin hydrodynamics. This is from this paper we had this year in collaboration with Masaru Hongo, Kaminski, Bishan, Stefanov, and Huang this year. The non-conservation of spin current can bring another problem. That is the definition of the spin is not unique. So there is an ambiguity in defining the spin current. This ambiguity is sometimes called the pseudo-gauge ambiguity. So the pseudo-gauge transformation is given by the following way. So you have the spin current. If you minus a function phi, which has the same symmetry as the spin current, and if you add another part to the energy momentum tensor given in this form constructed by phi, so we will find that such transformation will preserve the total conserved angular momentum and total conserved energy and momentum, and also it preserves the conservation law. So which means the quantities on both sides are qualified to be spin. Here, the quantity on both sides are qualified to be energy momentum tensor. Yeah, this pseudo gauge transformation is not a true gauge transformation. So, namely, both sides in this formula could be observable. So, namely, we need to choose what to observe, and then determine what would be our operator to describe this observable. So, due to this ambiguity, the formulation of the spin hydro is also not unique. You can choose different form of the spin current and energy momentum current to construct different spin hydrodynamics. And those different spin hydrodynamics are not necessarily equivalent. They could describe different evolution of the system. Okay. Because as I said, the quantities connected by pseudo gauge transformation could be different observables. Okay, so you could formulate some different spin hydrodynamics. So here, indeed, there are already many papers discussing the spin hydrodynamics using different types of the spin current and energy momentum current. So that's to formulate the spin hydrodynamics. The first thing to do is to choose a pseudo gauge. So here we choose the pseudo gauge by coupling the spin to the torsion or the spin connection. So namely, we put the theory into a period space-time with torsion. And in this case, the energy momentum current can be given by the variation of the action with respect to the fair band E. And the spin current is given by the variation of the action with respect to the spin connection. So in this way, for example, for QCD, you can obtain those results. And you can find that in this way, the spin current sigma is given by the canonical form. And in this case, the equation of motion for the energy momentum tensor and the spin current just Wada Takahashi identity for the diffeomorphism and local nodes are invariants. These are the equation for motion. Okay, so then to to have the spin hydrodynamics, then step one is to identify what we want to include into the framework. So here we choose these 8 variables: the energy density, the U1 considered like the pion density, the velocity, the spin density. Totally 8 variables with the usual constraint. And also the local thermodynamics is given by here the first law of local thermodynamics. Okay, so with this first law, we can define the conjugate quantity to those densities. Those are the inverse temperature, chemical potential, and the spin chemical potential. And then we need to give the speed, the power counting scheme. So here we treat this temperature, density, pion density, velocity, and the field as the 0th order quantity. But the spin chemical potential, spin density, and the spin connection as the 1st order ingredient. So the step 2 is to make the tensor decomposition of the energy momentum tensor and the spin current. So here, that's the usual decomposition. But here you have you see that there is an unusual quantity delta Q mu, and also an unusual quantity delta sigma. So what we want is finally we need some constitutive relation between this delta theta mu a and also the gradient of velocity, temperature, and so on, and also a condition similar relation for delta Q. Yeah, but actually this delta Q mu is redundant, because if you apply this Watanabe-Hash identity, you can realize that the delta Q is not a dynamic current. It is determined by the spin current. So finally, we calculated the entropy production rate, which is given by this formula, and apply the second law of local thermodynamics, which requires that the production rate of entropy is positive. This fixes the form of the delta theta mu a. So the symmetrical part is given by the usual shear viscosity and the bound viscosity. But the anti-symmetrical part is given by this anti-symmetric form with a new transport coefficient called the rotational viscosity. Okay, so those with this substitute this relation into the Watanabe-Hash identity, we get an equation motion of the hydrodynamic mode that those would be the hydrodynamic equations. If suppose we also know the relation between pressure and those hydrodynamic quantity, energy density, pion density, and spin density. This is the equation of state. The set of equation will be closed, and this is a complete form of the spin hydrodynamics with a given initial condition. This set of equations will tell us how the temperature, velocity, and spin polarization evolve in time. Okay, so in future, I think there will be a lot of things that are needed to be done. For example, we need to formulate a causal and a stable spin hydrodynamics. So far, we have this first order spin hydrodynamics, which we do not impact that it is causal and numerically stable. And also, it could be interesting to consider how the frame choice and the pseudo choice are connecting different formulations of the spin hydrodynamics. It could be also interesting to calculate the new transport coefficient, the rotational viscosity. For the QCD, this could give insight to the QCD spin dynamics, and this new transport coefficient could also be provide some new playground for example, the holographic calculations. It could also be interesting to formulate the spin hydrodynamics with magnetic field and anomaly. Recently, there are some interesting work trying to derive the spin hydrodynamics from the kinetic theory. I think finally it's very important is to apply the spin hydrodynamics to do some numerical simulation for example, the polarization. So here, I just give you a picture that if we do the calculation, what we expect to see. So the spin would flow with the fluid. That's because the fluid would be expanding in this direction strongly. We expect that the spin polarization will also move strongly in this direction. This is actually qualitatively consistent with what observed in the experiment. That's quite promising that using the spin hydrodynamic simulation, we could get some insight into the local spin. Because this vorticity and the spin is quite inspiring to consider how the rotation can also influence the phase structure of QCD. So if you write down the Hamiltonian, you can realize that the rotation plays similar role as a temperature potential, the interesting effect of rotation is that it could polarize the spin. Thus, this favors the spin zero condensate, like the Carroll condensate, so that under rotation, the Carroll condensate is tending to be destroyed. This could lead to some interesting phase diagram. For example, this schematic phase diagram that with rotation as a new axis, the usual phase diagram is extended to a three-dimensional phase diagram with some special phase could emerge. So with this, I summarize. So we see that a global and a local spin polarization of hadrons are observed in hadron collision experiment, and we see that the vorticity interpretation for global spin polarization works quite well, but it does not work for the local spin polarization. And it will be important to have a dynamic theory for the spin degrees of freedom, and now with the spin proof-right formula and also this dynamic theory for spin degrees freedom, we could have a complete description of the spin evolution in hadron collisions. And also the rotation could introduce some new integrated phase structure of QCD. Okay, so with this, I thank you very much for your attention.
Thank you. Thank you for a nice presentation. Now we will have some time for questions. So in the audience, if you have a question, please raise your hand and we will go in the order of those hands. And since I don't see any yet, let me start with my question first. So one of the things that was kind of bothering me was this spin hydrodynamics. When you are going to consider spin density, in principle, in quantum field theory, you would find that J5, the axial current, is directly related to the spin polarization. So it seems to me like the spin hydrodynamics should be exactly the same as the Carroll hydrodynamics, where you simply introduce additional current density J5. But what you are showing seems to be very different. So I'm trying to understand why there is a difference and what is Carroll hydrodynamics not going to capture if you associate J5 with the spin density.
Yeah, that's a very good question. Yeah, as you said, this spin current sigma mu AB is determined by the Carroll current. This sigma C plus delta sigma U C is J5 mu, J5 C. However, the difference is that in the J5 case, what is the charge J5 0, but in the spin case, what is charge is the spatial part of J5. So namely, we take the spatial part of J5 as the density of a spin. So it's independent from the charge of J5.
Well,
we
it's
need
true.
to
It's independent because they are not conserved, and in principle, you could introduce dissipative terms in J5, and it seemed to be the same thing, no?
No. Okay. So for the J5, you need a dynamic. You need to describe the dynamics of the chiral charge that is given by partial mu J5 mu equal to something. This dynamic equation determines the dynamics of the chiral charge, not the spatial part of J5. Instead, in the spin hydrodynamics, what is determines is the dynamics of the spatial part of J5. So it has an additional dynamic equation.
Okay,
That's it. Yeah.
I see. Other questions? Okay, let's go through my list then. Regarding the lambda polarization in heavy ion collisions, I'm a little bit confused about the timing of creation of those lambdas with the given spins and the actual hydrodynamic equilibration, or essentially the formation of this hydra. Because in order to formulate spin hydrodynamics, you have to make sure that the spin is moving with the actual fluid, and it's at least almost equilibrated or in local equilibrium. So isn't that very different timing? The lambdas might be produced very early on, and if they're not captured much by the flow, basically they have nothing to do with the hydra. Isn't that right?
Yeah, that's a good question. Yeah, of course, if lambda produce very early, they don't need the spin hydra to describe. Yeah, that is true. But in fact, the lambda hydronization time is not short. It's not short.
Well, but that plays against it, because if it's long equilibration time, it never has a chance to equilibrate. That's the point.
Can you say it again?
Well, if the equilibration of lambdas with the hydrodynamics is taking long time, then basically it will never get a chance over a short existence of the fireball to equilibrate. So basically it's decoupled. It's not part of the hydrodynamics, it seems.
Okay, so the point is that the spin hydro does not necessarily to describe lambda. The spin hydro describes the it can use to describe the parton phase, and then the partons hydronize into lambda.
Oh, I see.
Like in the usual.
So basically, the lambdas are coming at the end, not at the beginning. But is that consistent with the general understanding how it happens?
At least this is consistent with, for example, if you want to calculate the lambda production in hydrodynamics, yes. In hydrodynamics, you first calculate how the fluid evolve in time, and then you use the Proof-Frey formula at some hypersurface to hydronize those fluid into hydrons. So here, very similar. First, we use the spin hydro to describe the medium evolution, and finally, we use this spin Cooper-Frey formula to hydronize spin into the spin.
So the lambdas are basically formed at the end of the evolution, not at the beginning or during. That's the
yes. Yes.
May I comment on this?
Go ahead.
Yeah, and I think that the lambdas which are formed at the end are around 64%. than the lambdas which are formed at the beginning from the experimental point of view. So statistically, I think means this is enough to say that 64% lambdas are more than the few percent at the beginning.
Okay, at the 200 GeV?
Yeah, 200 GeV, yes.
I see.
Well, but that's kind of troubling. If you have only 40% created at the end, basically majority of the signal is coming from somewhere else. No? Let me make sure that I understand it right. You're basically saying that only 40% are coming from this Cooper-Frye essential assumption. That's what you're saying, right?
No, I'm saying that 64% are coming from this, from the, means 64% of lambdas are forming after the freeze out or the hadronization.
Or during the freeze out.
Yeah, during the freeze out.
But 40% is a large number, and those discrepancies, it seemed to be that they are floating 100% back and forth. So,
okay, I'm not sure about the 40%. That 40% are actually coming from the beginning, or maybe it's left out in the process. But I'm pretty sure that 64% are actually coming during the freeze out. I mean, that is what I understood from the papers.
okay, I see. Any other questions then?
I have a naive question. So in your framework, you also consider that this mu, which is spin chemical potential or spin Lagrange multiplier, so to say, this is of derivative 1 order, which is equals to thermal vorticity.
Right.
I mean, at least order, right?
Right.
Okay.
Right.
And you believe that in the global equilibrium, these two will be equal?
This is not believe. This is derived. At the global, what is global equilibrium? Global equilibrium is given by the condition that this density operator is independent of the proper time that you choose the hypersurface.
Yes.
And this condition simply gives you that thermal shear should vanish, and the spin chemical potential should be equal to thermal vorticity.
Okay. Other questions? Other questions? Well, I cannot help, but I do have some more questions. When you were talking about the feed-down production of lambdas, the claim was that there are 80% of those lambdas coming from somewhere else, from other particles basically feeding down, but that only had a 10% effect on the spin polarization. Is there a clear, some kind of intuitive understanding why the effect is so little on the spin polarization?
Yeah, that's because if you see here, some decay channel will give you positive, but some decay channel will give you negative. Finally, all those contributions added together, they cancel each other. Only 10% effect remains. But of course, all those channels can produce the lambda, but their contribution to spin polarization just cancel each other.
Oh, so there is some sort of like lucky cancellations, you're saying?
Yeah, okay, right.
I see. Well, interesting. So only one, what is this second from the bottom line that is seemingly going to give a different, no, that's not the only one that is giving the other sign. Okay, I see. Anyway, never mind. I see. Okay, that's something I didn't really know, and it's pretty interesting. Okay, I don't see any other questions. Okay, there is one. Go ahead. Go ahead.
I may have missed it, but what is your opinion or perspective or reasoning behind the difference between this lambda and lambda bar polarization? The difference.
Right. Yeah. Yeah. As you know, one possibility is that there is a magnetic field contribution.
But don't you think that this can be? I mean, this magnetic field can be decayed in the process, and this might have no contribution.
This may not be. I think there are some numerical simulation showing that yeah, the magnetic field decay quite quickly, but there are still some. I mean, some magnetic field is remained at the time that the lambda is formed, and there are some numerical simulation that found that the magnetic field can contribute to not sensible, but can contribute to a difference between the lambda and anti-lambda. I mean, its contribution is not negligibly small, even though it's decaying fast.
Maybe to expand a little bit on that point, are there any other sources other than the magnetic field?
Right, yeah, there are some other sources. One source is the biochemical potential. Because you can see here at 200 GeV, the difference between lambda and lambda is very small. At the lower energy, this difference is more obvious. Although of course there are big error bar, but yeah, roughly you can see the difference. This is one possibility is ion density. Other possibility, there are some proposal that the formation of lambda and anti-lambda in the hydronic matter, the evolution, they will feel some other source from the vector meson, which can also give you some difference from the lambda. I think this is from Kapsta and Dolkovsky. Also, there was a paper from maybe from Dubna group discussing that the lambda and anti-lambda are formed in different space. For example, one can form the near rapid region, another from roughly in a larger rapid region. This way, they feel different magnitude of vorticity, and so that they can have a difference in polarization. There are several different possibilities.
Okay.
Yeah, but because the data, there is a big error bar. So I think if finally this error bar can be suppressed to let this lambda and anti-lambda polarization clearly separated, then I think we can test those models. So far, yeah, all those could be some possibility mechanism, but we cannot see which one should be the correct one.
Right. Okay. I don't see any other raised hands or any other people trying to ask questions. So let me use this opportunity and thank Xu-Guang for a very nice presentation.